At a distance of 2.5 million light-years, something gazes back in our direction. It is the Andromeda Galaxy, a vast spiral structure cradling 1 trillion stars. Deep within its luminous core resides a black hole with a mass equivalent to 140 million of our suns. The James Webb Space Telescope recently aimed its infrared vision into this galactic heart, and the resulting discoveries have fundamentally altered our understanding of this cosmic neighbor. Scientists found a dormant monster that appears to be stirring, along with ancient evidence of galaxies it has consumed and indications that the long-predicted collision with our own galaxy has, in a sense, already commenced. On a clear night in autumn, it is possible to spot Andromeda with the unaided eye, visible as a soft, hazy patch of light within the constellation Cassiopeia. Many who see it are unaware they are looking at an entire galaxy, a spinning disk of 1 trillion stars that stretches 220,000 light-years from one edge to the other. This is our closest major galactic companion, and it is on a direct course toward us. For more than a century, astronomers have dedicated themselves to studying this celestial island, meticulously mapping its spiral arms, cataloging its star clusters, and calculating its distance to be approximately 2.5 million light-years from our planet. While that span seems immense, on a cosmic scale, Andromeda is essentially in our local vicinity. The Milky Way and Andromeda are the 2 dominant members of a gravitationally bound cluster of over 50 galaxies, which scientists have named the Local Group. An astonishing detail, however, is that Andromeda is not stationary. It is hurtling toward us at a velocity of about 70 miles per second, which translates to more than 250,000 miles per hour. A speed of that magnitude would allow an object to orbit the Earth 10 times in just 1 hour. The galaxy has been on this trajectory for billions of years, and no force in the universe can alter its inevitable path. The arrival of the James Webb Space Telescope marked a turning point in our study of Andromeda. Unlike the Hubble telescope, which perceives visible light much like the human eye, Webb is designed to see in the infrared spectrum. This allows it to detect heat signatures and hidden cosmic structures that were completely invisible to all preceding telescopes. When Webb focused on Andromeda's central region, the scientific community anticipated observing a quiescent galactic center, a sleeping giant peacefully existing across the void. That expectation was incorrect. What Webb uncovered sent ripples of surprise throughout the field of astronomy. The images revealed activity stirring deep within Andromeda's heart, including unusual emissions of radiation, warped clouds of gas, and formations that current standard models of galactic evolution cannot explain. One researcher described the data as deeply unsettling, while another called it the most significant discovery about Andromeda in decades. The telescope captured details with a clarity no instrument had ever achieved before, showing filaments of superheated gas spiraling inward and dust rings aglow with infrared light. It also observed star clusters moving in ways that defied easy explanation. And there, at the very center, shrouded by layers of gas and ancient stars, was the behemoth itself, a supermassive black hole that may be in the process of reawakening. The implications of this are profound. If this black hole is indeed becoming more active, it could fundamentally reshape its host galaxy long before our 2 cosmic islands meet. The most startling part of Webb's discovery, however, is the suggestion that the collision between Andromeda and the Milky Way could be more turbulent, more chaotic, and arrive sooner than anyone had previously calculated. Human eyes are deceptive, showing us less than 1% of what truly exists in the universe. The visible spectrum, the familiar rainbow of colors we perceive daily, is merely a narrow sliver of the full range of electromagnetic radiation. Beyond the violet end of the spectrum lie ultraviolet rays, X-rays, and gamma rays. Beyond the red end are infrared, microwaves, and radio waves. The vast majority of cosmic events unfold in frequencies we can never see. This is where the James Webb Space Telescope plays its crucial role. Launched in December 2021, Webb does not view the universe in the same way we do. Its advanced instruments are specifically tuned to infrared wavelengths, allowing it to perceive the heat signatures of the cosmos. This capability gives Webb a unique power that Hubble lacked. It can see through the dense clouds of cosmic dust that completely obscure visible light. This is comparable to having thermal vision that can perceive heat through a dense fog, making the obstruction effectively transparent where normal sight would fail. When Webb aimed its 6.5-meter mirror toward Andromeda, it unveiled structures that had remained hidden for billions of years. Dust lanes that had always appeared dark and featureless in visible light images were suddenly seen blazing with infrared energy. It turns out these lanes are far from empty. They are densely packed with cool stars, vast molecular clouds, and the types of organic compounds that serve as the building blocks for new solar systems. The telescope employs two primary instruments to analyze the inner workings of galaxies. Its near-infrared camera, or NIRCam, captures exceptionally sharp images of stellar populations. Meanwhile, the mid-infrared instrument, known as MIRI, is designed to detect cooler objects such as dust, grains, and old, fading stars. Working in concert, these tools provide a comprehensive portrait of a galaxy's concealed anatomy. Yet, this is where the findings took an unexpected turn. As scientists analyzed Webb's infrared data from Andromeda's core, they observed something peculiar. There were temperature fluctuations that did not align with expectations. Some regions that should have been cooling were, in fact, growing warmer. Clouds of gas exhibited unusual patterns of movement, spiraling inward at a rate faster than gravitational models could account for. Subsequent observations confirmed the presence of dust rings encircling the galactic center, which were glowing brightly in mid-infrared wavelengths. These rings are not smooth or uniform. They show distinct gaps, distortions, and dense clumps, all of which point to significant disturbances in the recent past, within the last few million years, which is a mere moment in cosmic time. Webb also detected specific chemical signatures that had been entirely missed by previous telescopes. These included complex carbon molecules, organic compounds, and other elements that were forged in the cores of dying stars and then dispersed throughout the galaxy. This infrared spectrum functions almost like a chemical fingerprint, revealing the precise elements present and their relative abundance. The level of detail is extraordinary. Webb can resolve individual star clusters within Andromeda that appeared as little more than blurry smudges to Hubble. It can measure the temperature of gas clouds with a precision down to fractions of a degree, and trace the galaxy's spiral arms much deeper toward the core than ever before. However, with each new layer of detail, new questions arise. It seems the more clearly we are able to see Andromeda, the less we truly understand about the processes unfolding at its heart. At the heart of the Andromeda Galaxy, an unseen presence has long been suspected, and the Webb telescope has now given us our first meaningful look at its activities. What researchers have uncovered there overturns much of what was previously understood about quiescent black holes. On a galactic canvas, ordinary numbers start to lose their significance. The human mind cannot genuinely process the scale of 1 trillion. To illustrate, if you were to count one star every second, without pause for rest, it would require 31,700 years to reach that total. This is the approximate number of stars currently shining inside Andromeda. Each of these is a vast thermonuclear engine. The majority are smaller and cooler than our own Sun. A few are colossal blue giants, destined to detonate in just a few million years. Still others are ancient red dwarfs, fated to burn for trillions of years into the distant cosmic future. All of these stars are bound in orbit around a shared center of mass, held in place by the invisible influence of dark matter, which outweighs the stars themselves by a ratio of 6:1. The James Webb Space Telescope has the power to resolve specific, individual stars within Andromeda's outer territories. It cannot, of course, distinguish all of them. Such a feat would be impossible, but Webb is capable of identifying the most brilliant giants, massive stars, that radiate with the energy of 10,000 or even 100,000 of our suns. These stellar lighthouses act as crucial reference points, enabling scientists to chart the galaxy's architecture with an unprecedented level of detail. The Hubble Space Telescope photographed more than 200 million stars in Andromeda over a survey that spanned more than a decade. Those observations were pieced together to form the most intricate mosaic of another galaxy ever created. Hubble, however, operates mainly in the visible light spectrum. It captured the bright, young stars, but was blind to countless others that were concealed behind veils of dust. Webb is now completing that picture, unveiling the cool red giants and the dusty stellar nurseries where new suns are being born. The process of star formation in Andromeda unfolds differently than it does in our own Milky Way. Our galaxy gives birth to approximately 7 new stars each year. Andromeda, in contrast, produces fewer, perhaps only 2 or 3. Scientists have theorized that this disparity is a consequence of Andromeda's turbulent past. The galaxy seems to have experienced a major collision several billion years ago, an event that likely consumed a large portion of its available gas. With a diminished supply of raw materials, fewer stars are able to form. Yet, Webb has uncovered something quite unexpected. It appears that specific areas within Andromeda are generating stars at surprisingly high rates, far surpassing what existing models had predicted. These stellar nurseries are tucked away inside the spiral arms, enshrouded in thick cocoons of dust that are impenetrable to telescopes that see invisible light. Webb's infrared vision cuts right through them. The temperature data is especially illuminating. Newly formed stars are intensely hot, bathing their immediate surroundings in ultraviolet radiation. This energy warms the nearby dust, causing it to emit a glow in infrared wavelengths. Webb can precisely measure this glow and then calculate the number of young stars that must be responsible for it. In several key regions, these numbers are significantly higher than anticipated. The question then becomes why certain parts of Andromeda would suddenly exhibit such heightened activity. One leading theory suggests gravitational interactions with its satellite galaxies. As a smaller galaxy makes a close pass by Andromeda, its gravity can compress clouds of gas, setting off intense bursts of star formation. An alternative theory proposes that Andromeda's own spiral arms generate compression waves that periodically squeeze interstellar gas into dense, star-forming clumps. The sheer quantity of mass contained within all these stars is difficult to fathom. Andromeda holds about 1.5 trillion times the mass of our Sun, a figure that includes both the stars themselves and the vast dark matter halo that envelops them. For comparison, the Milky Way contains only about 800 billion solar masses. This makes Andromeda nearly twice as massive as our home galaxy. The difference in size is of great consequence. When two galaxies collide, the more massive one typically dictates the outcome. And in 4 billion years, when these two cosmic titans are set to meet, Andromeda will be the larger of the two. But there is something else concealed at the center of all those stars, an object that dwarfs the trillion burning spheres. At the precise core of Andromeda, within a space smaller than our own solar system, lies an object with a mass equivalent to more than 100 million suns combined. It is entirely invisible and emits no light of its own. It is a supermassive black hole. And for almost all of human history, it has been quiet. Black holes do not truly sleep, but their activity level can be described as either quiet or loud, depending on the amount of material they are consuming. When a black hole is actively feeding on gas and stars, it can become one of the most luminous objects in the cosmos. The matter spiraling inward is heated to millions of degrees, forming a brilliant accretion disk that radiates intensely across the entire electromagnetic spectrum, from radio waves to gamma rays. Astronomers refer to these as active galactic nuclei. and they possess the power to outshine their entire host galaxy. Andromeda's black hole is not currently in such a state. For millions of years, it has been categorized as dormant. It sits silently, warping space-time into a gravitational well from which nothing can escape, only occasionally consuming a stray cloud of gas or an unfortunate star. The radiation it emits is faint and barely perceptible, even to powerful X-ray observatories. Scientists have often compared it to Sagittarius A*, the supermassive black hole at the center of the Milky Way, which is also known for being exceptionally quiet. This picture began to change with a series of X-ray observations. The Chandra X-ray Observatory has been monitoring Andromeda's core since the year 2000. For more than 15 years, it registered a consistent but faint X-ray signal emanating from the central black hole. Periodically, this signal would spike, creating a brief flare that might last for hours or days before returning to its baseline level. These flares occurred every few years and appeared to be random. In 2006, Chandra registered an unusually powerful flare. The X-ray brightness surged by a factor of 100, flooding the central region with high-energy radiation before it subsided once more. At the time, scientists noted the event as interesting but not necessarily alarming, reasoning that black holes sometimes have outbursts. Perhaps a small gas cloud had fallen in, or a star had ventured too close. But then, in 2013, it happened again, another intense flare. And on this occasion, it was accompanied by something strange. The IceCube Neutrino Observatory in Antarctica detected a burst of neutrinos originating from the direction of Andromeda. Neutrinos are ethereal particles that rarely interact with matter, produced only in the most extreme environments where matter is subjected to unimaginable forces. The correlation was deeply intriguing. 2 X-ray flares and 2 neutrino bursts, all appearing to come from the same source, suggested that something truly violent was taking place at Andromeda's core. A recent analysis, published in 2025, has confirmed that the black hole has remained in an elevated state of activity ever since 2006. Its baseline X-ray emissions are now higher than they were previously, and the flares have become more frequent. This new, more active state is now confirmed by the data. A noticeable change has occurred in the central black hole of Andromeda, which is now behaving in a way that differs from its state 20 years ago, prompting the question of what is causing this shift. One leading explanation suggests that the Andromeda Galaxy may have recently drawn in a dense cloud of gas, or perhaps even the remnant of a small galaxy. The inward spiral of this captured material would create the precise kind of elevated energy output that researchers are currently observing. An alternative theory presents a more unsettling possibility, that the black hole is merely entering a naturally active period in its life cycle. This would imply that what we have considered a dormant state might only be a temporary period of quiet before a much more active phase. If this great object is truly awakening, the effects would reverberate throughout the entire galaxy. Powerful jets of radiation could potentially erupt from Andromeda's core, and the rate of star formation could be either suppressed or ignited, depending on the event's intensity. Looking far into the future, when the Milky Way is set to collide with Andromeda billions of years from now, our distant descendants might inhabit a cosmos dominated by 2 active supermassive black holes instead of just one. The James Webb Space Telescope has contributed another significant element to this unfolding mystery. Its observations in the infrared spectrum have uncovered a detail that the Chandra Observatory could not perceive. Gas clouds in the vicinity of the black hole are moving at speeds greater than they should be. Some unseen force is causing them to accelerate. And the most profound question of all has yet to be answered. If this black hole is beginning to stir now, what will it be like when it reaches its full active potential? Mass has the power to bend reality itself. When a sufficient amount of matter is compressed into a small enough volume, it can tear a hole in the very fabric of space-time. Such an object resides at the heart of Andromeda, a supermassive black hole with an estimated mass of 140 million times that of our Sun. To grasp the scale of this entity, it helps to consider the black hole at the center of our own galaxy. Known as Sagittarius A*, it weighs approximately 4 million solar masses, an object already beyond easy comprehension. It is already powerful enough to send stars careening through space at thousands of miles per second. Andromeda's black hole is 35 times more massive than ours. The event horizon, which marks the boundary of no return around a black hole, grows in proportion to its mass. For Sagittarius A*, the event horizon has a radius of about 12 million miles. One could place 17 stars like our Sun side by side to span that distance. The event horizon of Andromeda's black hole is roughly 35 times larger in comparison. The vast region of gravitational influence surrounding it measures over 400 million miles in diameter, a distance greater than the orbital path of Mars. Anything that ventures across this threshold is lost forever. It would not be instantly annihilated, as is often depicted in science fiction, but would instead be stretched and torn apart by immense tidal forces during its inward spiral. This process is known to physicists as spaghettification. A person falling toward the black hole would experience a gravitational pull on their feet so much stronger than on their head that they would ultimately be pulled into a thin stream of individual atoms. For now, however, nothing appears to be falling in. The region immediately surrounding Andromeda's black hole is surprisingly vacant, which is the reason it remains so quiet. A black hole that lacks a source of fuel is essentially just a deep gravitational well sitting silently in the dark. Scientists were able to measure the mass of this immense object by observing the movement of stars near the galactic center. These stars travel at incredible velocities, whipping around a central point in elliptical orbits at thousands of miles per second. By carefully tracking their motion over many years, astronomers can precisely calculate the amount of mass required at the center to maintain such orbits. The result of these calculations was 140 million solar masses, with a margin of error of about 20 million. This uncertainty is a product of the phenomenal difficulty of measuring distances and speeds across the 2.5 million light-years that separate us from Andromeda. The black hole itself was first identified in 1991 with the aid of the Hubble Space Telescope. Hubble's sharp optical capabilities allowed it to resolve the very core of Andromeda, where it detected something unusual. The nucleus seemed to be double, with two bright clusters of stars separated by a mere 5 light-years. For many years, this observation sparked debate among astronomers. Some wondered if Andromeda was in the process of consuming a smaller galaxy, while others speculated it might possess 2 black holes. Subsequent observations eventually cleared up the confusion. The galaxy has only a single central black hole. The illusion of a double nucleus is created by an eccentric ring of stars that orbit it. These stars follow elongated, elliptical paths rather than circular ones, causing them to group together at certain points in their orbits. From our vantage point on Earth, this bunching effect gives the appearance of 2 distinct, bright cores. The reason for such peculiar stellar orbits is still a matter of investigation. The prevailing theory suggests that Andromeda's black hole may have merged with another one at some point in its past. When 2 supermassive black holes spiral together and ultimately collide, they unleash gravitational waves powerful enough to throw surrounding stars into more chaotic orbits. The available evidence points to such a merger having occurred perhaps a few 100 million years ago, though this remains a compelling theory rather than a confirmed fact. What is certain is the black hole's mass and its potential appetite. And what scientists are now beginning to see, largely thanks to the Webb telescope, is that new material is starting to make its way toward this sleeping giant. Thin streams of gas are slowly falling toward the center, not yet enough to fully awaken the black hole, but sufficient to cause it to simmer at a higher level of activity than before. The simple question on everyone's mind is how much longer it will be until it rouses completely. Black holes do not behave like indiscriminate cosmic vacuums, swallowing everything in their vicinity. They are, in fact, remarkably selective feeders. For material to fall in, it must first lose its angular momentum, which means that gas and dust need a way to shed their orbital energy. This occurs through processes like friction, magnetic fields, and gravitational interactions, resulting in a slow, spiraling descent into oblivion. The James Webb Space Telescope has provided a clear picture of exactly how Andromeda's black hole is being fed. It revealed long filaments of gas and dust that extend from the outer parts of the galactic center, winding inward in elegant, spiraling patterns. While these structures have always existed, previous telescopes did not have the necessary resolution or infrared sensitivity to see them with such clarity. Webb has changed that. These filaments are visible in infrared light because they are warm. As the gas descends toward the black hole, friction causes it to heat up. The material rubs against itself, reaching temperatures of thousands of degrees. This is still quite cool when compared to the millions of degrees found closer to the event horizon. But it is hot enough to glow brightly at the infrared wavelengths that Webb is designed to detect. Scientists using combined data from the Hubble and Spitzer space telescopes had previously caught glimpses of these structures, but Webb's images offer the most definitive view to date. The filaments resemble celestial streams, with matter flowing toward the center from multiple directions. Some of this material originates from dense molecular clouds within the galactic disk, while other streams come from star clusters that were disrupted after wandering too close. The feeding process itself is not a steady flow. It appears to happen in intermittent bursts. A substantial mass of gas spirals inward over a period of weeks or even months, triggering a brilliant flare of radiation. Afterward, the black hole settles back into dormancy, awaiting its next opportunity to feed. This cycle is well documented by X-ray telescopes, which have recorded sporadic outbursts every few years. What makes the current era so distinctive is the noticeable increase in the regularity of these events. It appears that over the last 2 decades, the black hole has been engaging in these feeding events with greater frequency. This observation strongly suggests a change has occurred within the galaxy's central region. One possibility is that gravitational nudges from Andromeda's satellite galaxies are now channeling a greater supply of gas toward the core. Another is that the galaxy's own spiral arms are compressing interstellar material and directing it inward. Data from the Webb telescope has added another layer of complexity to this picture. An intriguing detail is that some of the gaseous filaments are moving with unexpected velocity. While it is normal for gas to accelerate as it nears a black hole, the speeds being measured are greater than what gravity alone can account for. This hints that other forces must be involved. Perhaps powerful magnetic fields are guiding the gas along particular pathways, or maybe jets of matter are being ejected from the black hole's poles, creating pressure waves that disturb the surrounding gas. Very close to the center, within just a few light years of the black hole, these filaments dissolve into chaos. The structured spiral pattern gives way to a storm of turbulent eddies and swirls. This is the accretion zone, a region where matter travels at a significant percentage of the speed of light, is superheated to millions of degrees, and is violently stretched apart by immense tidal forces. Even an instrument as powerful as Webb cannot resolve the fine details so near the event horizon. The area is simply too compact and intensely bright. The story, however, is clearly told by the outer filaments. For the moment, the black hole is being fed by a gentle stream rather than a powerful deluge. And yet, the rate of this feeding is on the rise. More gas is reaching the center today than it was a century ago. Should this trend persist, Andromeda's central black hole could transform from a dormant giant into a moderately active one within the next several million years. On a cosmic timescale, this is remarkably soon. For our own species, it lies so far in the future that humanity may no longer be here to see it. That is, unless the feeding rate increases more rapidly than current models predict, or if a sudden, catastrophic event were to funnel a truly massive quantity of material into the core, and in a few billion years, when the Milky Way merges with Andromeda, that is precisely the scenario that will unfold. When the Hubble telescope first imaged Andromeda's center in 1991, the pictures presented a genuine puzzle to astronomers. Instead of a single, brilliant nucleus, the images showed two separate concentrations of light, divided by a distance of about 5 light-years. The brighter of the two, designated P1, is located slightly away from the geometric center. The fainter one, named P2, occupies the galaxy's true central point. For many years, this dual nucleus was the subject of intense scientific discussion. The prevailing theory proposed that Andromeda had recently absorbed a smaller galaxy, and P1 was the surviving core of that consumed galaxy. This would be a captured nucleus, orbiting the true center before its inevitable disruption and absorption. It was a compelling narrative that aligned with our understanding of how large galaxies grow by consuming smaller ones. This explanation, however, was not without its problems. If P1 were indeed a captured galactic core, it should be highly unstable. The immense tidal forces from Andromeda's primary black hole would tear it apart in only a few million years. Yet observations showed P1 to be intact and coherent. The timeline simply did not add up. Subsequent observations with more advanced instruments eventually uncovered the real story. P2, the dimmer of the 2 points of light, is the actual location of the supermassive black hole. This black hole is encircled by a dense disk of hot, blue stars. These are young, massive stars of spectral class A, which radiate powerfully in ultraviolet light. Consequently, in images taken in blue and ultraviolet wavelengths, P2 actually outshines P1. Conversely, in red and infrared light, P1 is the dominant feature. So what exactly is P1? The solution proved to be far more fascinating than a captured galaxy. P1 is an optical effect created by a vast, eccentric disk of stars orbiting the central black hole. The stars within this disk do not follow simple circular paths. Instead, their orbits are highly elongated ellipses. As they travel around the black hole, they tend to cluster together at their apocenter, the point in their orbit that is farthest away. This congregation of stars creates a dense, bright region that appears to be a separate nucleus. One can visualize this by imagining stars moving along these stretched orbits, where they naturally slow down and bunch up at the farthest extent of their journey, creating a temporary bright spot. But what could cause stars to adopt such unusual orbital patterns? The most widely accepted explanation involves gravitational recoil from a past black hole merger. When two supermassive black holes spiral into one another and combine, they emit powerful gravitational waves. These waves are not symmetrical. They carry momentum away from the system. If the original black holes had different masses or spins, the newly formed, merged black hole can receive a substantial kick in one direction. This sudden displacement violently disrupts the orbits of nearby stars, throwing them into the kind of eccentric paths we now observe. This scenario is strongly supported by computer simulations. When scientists model a black hole merger at a galaxy's heart, the resulting distribution of stars bears a striking resemblance to the structure seen in Andromeda's core. The merger itself would have taken place several 100 million years ago, which is long enough for the system to achieve a degree of stability, but not so long that the eccentric orbits have had time to circularize. This implies that Andromeda's central black hole is itself the result of a cosmic collision. It was likely born when two smaller black holes, each with a mass of tens of millions of suns, combined to form the current giant. And if Andromeda's black hole has already experienced one such merger, it is destined to have another in approximately 4 billion years. When our Milky Way and Andromeda finally collide, their central black holes will begin a long spiral toward one another. The 4 million solar mass black hole from our own galaxy will eventually meet the 140 million solar mass behemoth from Andromeda. Their collision will unleash gravitational waves of such immense power that they will warp the fabric of space-time across the universe. To fully appreciate this future, however, we must first understand how Andromeda grew into the titan it is today, and that requires examining the evidence of its long and turbulent past. Galaxies are not serene islands of stars, they are cosmic arenas governed by the relentless pull of gravity. In this environment, the strong inevitably consume the weak, and the large grow by devouring the small. Andromeda is a prime example of this process. It is a galactic cannibal that has been feeding on its neighbors for billions of years. The proof of this history is imprinted within the galaxy's own stellar populations. Astronomers who study these populations have uncovered something extraordinary. Andromeda's brilliant spiral disk is enveloped by a vast, faint cloud of old stars, its outer halo. Within this sphere are distinct currents of stars, moving in organized patterns. These streams are not random. They are the dismantled remains of smaller galaxies captured and torn asunder by Andromeda. When a dwarf galaxy enters the gravitational field of a giant like Andromeda, tidal forces stretch it into a long filament. Its stars are stripped away over millions of years, spreading out along its orbital path. Eventually, the dwarf galaxy disappears completely, its stars absorbed into the halo of the larger galaxy. The resulting stream, however, can persist for billions of years, an ethereal marker of a vanished galaxy. Scientists using the Hubble Space Telescope mapped dozens of these stellar streams in Andromeda's halo. Analyzing the age and chemical makeup of the stars in each stream allowed them to reconstruct the galaxy's history of assimilation. The findings were staggering. Andromeda has consumed at least 100 to 200 smaller galaxies over the past 12 billion years. Some were tiny dwarf galaxies with only a few million stars. Others were substantial spirals with billions. The most significant merger happened relatively recently in cosmic terms, just a few billion years ago. This collision brought a massive influx of stars and gas, triggering bursts of star formation and reshaping Andromeda's structure. Evidence for this event shows up in the ages of stars. Many of Andromeda's stars are between 2 and 4 billion years old, suggesting a major episode of star birth in that period. But there was another merger, much older, that happened roughly 10 billion years ago. This ancient collision involved a galaxy perhaps 1/5 the mass of the Milky Way, a substantial meal. The stars from this merger now form part of Andromeda's inner halo, a spherical cloud of old, metal-poor stars surrounding the galactic center. Chemical signatures clearly tell the story. Stars born in small dwarf galaxies have different element ratios than stars born in large galaxies. Smaller galaxies build stars slowly, enriching them mainly with elements from long-lived, low-mass supernovae. Larger galaxies, however, form stars rapidly, so their stellar populations also contain elements from massive, short-lived supernovae. By measuring these ratios in Andromeda's halo stars, astronomers can identify which galaxy each star originally came from. This data is confirmed, the stellar streams exist, and the chemical evidence is unambiguous. Andromeda has been piecing itself together through these cosmic mergers for over 10 billion years, a process that has not yet ended. Right now, several dwarf galaxies orbit Andromeda, their fates sealed. Over the next few billion years, they will spiral inward, to be stretched and torn apart by tidal forces until nothing remains but new streams in the halo. Andromeda will continue growing, feeding, preparing for its ultimate collision. The Milky Way is not innocent either. Our galaxy has its own history of cannibalism. We are currently consuming the Sagittarius dwarf elliptical galaxy, a small system that has already made multiple passes through the Milky Way's disk. We will finish eating it within the next few 100 million years. But when Andromeda and the Milky Way finally meet, it will not be a small galaxy devoured by a large one. It will be two titans locked in mutual transformation. Both galaxies will be forever changed, and the scars they leave on each other will persist for billions of years. The ghosts of dead galaxies are watching. They know what comes next. It is as if a city were dismantled, its pieces scattered across a vast landscape. An investigator arriving later could still understand what happened by carefully mapping the patterns in the wreckage. This is what astronomers do when they study galactic halos. Andromeda's halo extends far beyond its bright spiral disk, stretching outward for hundreds of thousands of light-years, a vast, nearly invisible sphere of old stars and dark matter. This halo contains the memories of every galaxy Andromeda has ever consumed. Using deep imaging from the Hubble Space Telescope, a team of astronomers catalogued the globular clusters in Andromeda's halo. Globular clusters are dense spheres of ancient stars, typically containing hundreds of thousands of members, packed into a space just a few dozen light-years across. They orbit galaxies like satellites, immune to the chaos of the galactic disk below. Andromeda has over 400 of these clusters, far more than the Milky Way's roughly 150. Each cluster tells a story. By measuring how fast it moves and in what direction, astronomers can trace its orbit backward in time. Clusters orbiting in similar planes and at similar speeds likely came from the same original dwarf galaxy. The halos of consumed galaxies do not disappear immediately. When Andromeda tears apart a dwarf galaxy, the victim's dark matter halo, its globular clusters, and its stars all get redistributed. For billions of years, however, they maintain a degree of coherence, moving as a collective in patterns that reveal their shared origin. A pivotal 2019 study revealed something remarkable. Andromeda's globular clusters fall into two distinct populations. One group orbits in a relatively flat plane, moving in the same direction as the main galaxy's rotation. These are likely native clusters born when Andromeda itself formed over 12 billion years ago. The other group moves on wildly inclined orbits, some even going in the opposite direction. These are the invaders, clusters captured from smaller galaxies. But it gets more specific. The captured clusters themselves split into two subgroups based on their orbits and ages. One subgroup appears to be the remnants of a merger that happened roughly 2 billion years ago. The other subgroup is much older, dating back to a merger around 10 billion years ago. Two distinct cannibalistic events, each leaving a unique signature in the halo. This is galactic archaeology. By studying the present-day distribution of stars and clusters, scientists reconstruct the violent history that created the galaxy we see today. It is like excavating ancient ruins to understand a civilization that disappeared millennia ago. The stars in these ghost halos are metal poor, meaning they contain fewer heavy elements than stars born recently. This makes sense. Small dwarf galaxies form stars slowly, so they do not produce as many heavy elements through supernovae. When Andromeda drew in and absorbed smaller galaxies, it also inherited their populations of metal-poor stars, which now populate its vast outer halo. The story of this galactic history has gained new detail thanks to the Webb telescope's infrared observations. By gauging the temperatures and chemical makeups of individual red giants within the halo, astronomers can establish their ages with greater precision. Some of these stellar relics are over 12 billion years old, making them nearly as ancient as the universe itself. Others are significantly younger, just a few billion years old, born during mergers that occurred in the more recent cosmic past. The spatial arrangement of these stars also tells a story. Those from the most recent merger remain concentrated in specific areas of the halo. In contrast, stars from the most ancient merger are distributed more evenly, a consequence of having billions of years to disperse. This evidence paints a clear portrait of Andromeda as a serial predator of galaxies. It has spent its entire existence hunting and consuming its neighbors, and this behavior shows no signs of ceasing. At this very moment, multiple dwarf galaxies are trapped in its gravitational field, spiraling slowly inward to their destruction. The Milky Way is on a direct collision course with this galactic hunter. Yet, unlike the smaller galaxies Andromeda has consumed before, our own galaxy has sufficient mass to be a formidable opponent. An intriguing question arises. What occurs when two predators of equal stature finally confront one another? More than 400 globular clusters orbit Andromeda, resembling a great swarm of ancient celestial objects. Each cluster is a dense city of stars, with hundreds of thousands gravitationally bound together in a sphere that could fit inside the space between our Sun and its nearest stellar neighbor. These clusters are artifacts from the early universe, having formed over 12 billion years ago during the assembly of the first galaxies. Indeed, globular clusters are among the oldest structures in the cosmos. The stars within them are metal poor, born before the universe was enriched with heavy elements from many generations of supernovae. They glow with a dim, reddish light, the signature color of aging giants that have burned through the majority of their hydrogen fuel. Andromeda possesses far more of these globular clusters than the Milky Way. Our galaxy is host to roughly 150 confirmed clusters. Andromeda, however, has over 400, and possibly closer to 500 when the faintest ones are accounted for. This difference is significant, as the number of globular clusters a galaxy has correlates with its history of mergers. More mergers lead to a larger collection of clusters. Each time Andromeda consumed a dwarf galaxy, it assimilated that galaxy's own globular clusters. Small dwarfs might contribute only a few, while larger ones could add dozens. Over billions of years of such conquests, Andromeda has amassed its enormous population. Andromeda's most massive globular cluster is designated B23G78. It holds several million stars and is thought to harbor an intermediate mass black hole at its core, weighing nearly 100,000 solar masses. This particular cluster is so dense and massive that it could be the stripped core of a small galaxy that Andromeda devoured long ago. When a dwarf galaxy is torn apart, its central nucleus can sometimes survive as a compact stellar remnant. Webb's observations are providing scientists with new methods for studying these clusters. Infrared imaging can penetrate the dense cores of globular clusters and resolve individual red giant stars. By measuring the brightness and color of these giants, astronomers can determine a cluster's age and chemical composition with unprecedented accuracy. The orbits of these clusters also help reveal Andromeda's dark matter distribution. Dark matter itself is invisible, but it exerts a gravitational pull on everything near it. By tracking how globular clusters move over years and decades, scientists can map the invisible dark matter halo that dominates Andromeda's total mass. This halo extends far beyond the visible galaxy, perhaps reaching 1 million light-years into space. But a curious and somewhat unsettling detail emerges from these motions. Some of Andromeda's globular clusters are moving faster than they should. Their high velocities suggest they are being influenced by gravitational perturbations from something that cannot be seen. The most probable explanation is ongoing interactions with infalling dwarf galaxies. As a dwarf galaxy spirals into Andromeda, its gravity tugs on nearby globular clusters, accelerating them into unusual orbits. This implies that the merger process is not merely a thing of the past, it is an active, ongoing event. Andromeda is currently in the process of consuming at least one, and possibly several, small galaxies. These victims exist in various stages of destruction. Some are still mostly intact, recognizable as distinct celestial objects. Others have been stretched out into long stellar streams that span hundreds of thousands of light-years. Eventually, all of them will dissolve into Andromeda's halo. The clusters, however, will survive. Globular clusters are incredibly resilient. Their stars are packed so tightly that the cluster holds together, even when subjected to intense tidal forces. They can pass directly through a galaxy's disk and emerge on the other side intact. The eventual collision between Andromeda and the Milky Way will cause the globular clusters from both galaxies to intermingle, forming a new combined population that will number over 500. For now, these ancient clusters orbit Andromeda as silent testimony to the galaxy's violent history. They are like gravestones for dead civilizations, markers for galaxies that no longer exist, and they serve as a preview of what awaits the Milky Way. When our galaxy falls into Andromeda's gravity, our globular clusters will join its own, swirling together in the merged halo of a new cosmic monster. The Great Collision has not yet begun. Or has it? Andromeda does not travel through space in isolation. It is accompanied by an entourage of at least 14 confirmed satellite galaxies, with potentially more waiting to be discovered. These small galaxies orbit the larger one, trapped in its gravitational field and slowly spiraling toward their inevitable demise. The largest and most famous of these satellites is Messier 32, a compact elliptical galaxy that orbits Andromeda at a distance of about 24,000 light-years from its center. Messier 32 is an unusual object. It looks like the stripped core of a much larger galaxy. Its outer regions appear to have been torn away, leaving only the dense central bulge. Scientists theorize that Messier 32 was once a substantial spiral galaxy, but repeated close passes through Andromeda's disk have shredded its outer stars and gas. Another prominent satellite is Messier 110, a dwarf elliptical galaxy with a smoother and more intact structure. It orbits farther out than Messier 32, at roughly 190,000 light-years from Andromeda's center. Messier 110 still contains some young stars, which is evidence of recent star formation and an uncommon trait for an elliptical galaxy. Gravitational influence from Andromeda might explain how gas clouds inside Messier 110 became compressed, setting off episodes of stellar birth. Beyond these, more prominent companions are the ultra-faint dwarf galaxies. These are remarkably small systems, home to just a few thousand stars, which makes them exceedingly difficult to find. What is remarkable is their composition. They are thoroughly dominated by dark matter, which can outweigh the visible stars by factors of 100 to 1, or sometimes even more. It was only within the last 2 decades that astronomers managed to identify many of these dim companions, a feat accomplished through deep sky surveys using powerful, modern telescopes. The orbits of these satellite galaxies are not haphazard. A significant number of them travel together within a coherent, thin disk, a plane of galaxies moving in more or less the same direction. This alignment, known as the Great Plane of Andromeda, has been a long-standing puzzle for astronomers. This raises a compelling question. What process would lead satellite galaxies to organize themselves into such a structured formation? One hypothesis proposes that they are the surviving fragments of a much larger structure that was torn apart by Andromeda's gravity. It is conceivable that a filament of galaxies was drawn into Andromeda's gravitational field along a particular path, resulting in the planar distribution observed today. An alternative explanation points to the tidal forces exerted by our own Milky Way, suggesting they could be responsible for pulling Andromeda's satellites into their current arrangement. Whatever their origin story, the ultimate destiny of these small galaxies is certain. Over immense timescales, gravitational interactions will bleed away their orbital energy. This will cause them to spiral inward, their paths taking them progressively closer to Andromeda's galactic center. In time, powerful tidal forces will shred them completely, scattering their stars throughout Andromeda's vast halo. For several of these satellites, this destructive process is already in motion. Astronomers have detected stellar streams trailing away from them, which serve as clear evidence that they are being actively dismantled. The James Webb Space Telescope has the capability to resolve individual stars within some of these satellite galaxies. An analysis of their ages and chemical makeup offers scientists clues about the cosmic environment where they originally formed. Dwarf galaxies are essentially fossilized relics from the universe's infancy. They came into being very early and, for the most part, ceased producing new stars long ago. Their stellar populations are consequently ancient and poor in heavy elements, offering a unique glimpse into the conditions that prevailed more than 12 billion years ago. An intriguing detail is that some of Andromeda's satellites show signs of having been influenced by reionization. This was a pivotal cosmic event that occurred around 13 billion years ago, when the first stars and galaxies bathed the cosmos in ultraviolet light. That intense radiation ionized the neutral hydrogen gas spread throughout space, which made it much more difficult for small galaxies to retain their own gas reserves. As a result, star formation halted in many dwarf galaxies during this era, leaving them preserved in time as artifacts of the early universe. The gravitational dance between Andromeda and its many satellites has been playing out for billions of years. Some companions have already been entirely absorbed. Others are now in the final phases of their disruption. A small number might endure for another billion years before they too are consumed. Here in the Milky Way, we possess our own contingent of satellite galaxies, which includes the large and small melanic clouds. When Andromeda and the Milky Way finally merge, their respective satellite systems will also combine. The survivors of this cosmic event will then orbit the newly formed, larger galaxy, provided they are not ejected into the void of intergalactic space by the sheer force of the collision. However, an even more profound discovery has recently come to light. The collision between our galaxy and Andromeda is not some far-off occurrence. In a tangible way, it is already happening. For many decades, the Andromeda collision was framed by astronomers as a remote future event, something set to unfold in 4 billion years. It was viewed as a cosmic spectacle so distant in time that it held no immediate relevance for humanity. That description is no longer considered accurate. In 2020, a team of scientists involved with Project Omega announced a startling finding. The name AMGA is an acronym for Absorption Map of Ionized Gas in Andromeda, a research initiative that employs the Hubble Space Telescope to investigate the galaxy's halo. While charting the immense gaseous cloud that envelops Andromeda, they uncovered something wholly unexpected. The halo was discovered to be vastly larger than anyone had previously imagined. Andromeda's halo, a sphere of hot, ionized gas, reaches outward for approximately 1.3 million light-years from the galactic center in every direction. This constitutes an enormous envelope of tenuous plasma, heated to temperatures that reach hundreds of thousands of degrees. This gas is imperceptible to conventional telescopes and can only be identified by how it absorbs ultraviolet light from background sources. The Milky Way is surrounded by a comparable halo, a massive cloud of hot gas and dark matter that extends well beyond our galaxy's visible disk. The latest measurements indicate that our own halo also has a radius of roughly 1.3 million light-years. The significance of this is clear. Andromeda is positioned only 2.5 million light-years away. When two galaxies each have halos extending 1.3 million light-years in all directions, their outer edges must inevitably meet. In fact, it is now believed they have been in contact for more than 1 billion years. This conclusion is supported by observational data. The merger between the Milky Way and Andromeda has already commenced. We are, at this moment, moving through the outermost regions of Andromeda's halo, just as it is passing through ours. The interaction is so gentle that it goes completely unnoticed. The gas within these halos is incredibly diffuse, with a density of just a few atoms per cubic meter, and it exerts no discernible drag on the galaxies. Yet the implications of this contact are immense. These two great cosmic islands are not isolated objects traveling through empty space. They are fundamentally bound to one another by gravity, caught in an inexorable dance that will culminate in a merger. The halos are merely the first parts to make contact. Over the next few billion years, this interaction will grow stronger. The regions where the halos overlap will become compressed and will heat up. Eventually, the visible disks of the two galaxies will start to warp under the influence of their mutual gravity. Computer simulations provide a roadmap of what will happen next. In about 2 billion years, Andromeda will appear much larger in the night sky of Earth, assuming our planet still exists and has a life-supporting atmosphere. The galaxy will span tens of degrees, presenting a breathtaking spectacle that will command the heavens, but it will not be a tranquil sight. By that time, tidal forces from Andromeda will be actively distorting the spiral arms of the Milky Way. Then, in approximately 3.7 billion years, the first close pass will occur. The two galaxies will swing by one another, their disks starting to interpenetrate. This event will ignite tremendous bursts of star formation as vast clouds of gas collide and are compressed. The night sky will be set ablaze with millions of brilliant, blue newborn stars illuminating emission nebulae across enormous stretches of space. Following this initial passage, the galaxies will pull away from each other again, their mutual gravity having locked them into elliptical orbits. But there will be no escape. In approximately 1 billion years, the two galaxies are projected to meet again, this time in a far more chaotic encounter. The graceful spiral architectures that define them would be completely dismantled, with stars being cast out in every direction. Some solar systems might even be thrown into the vastness of intergalactic space, becoming galactic orphans. The merger process is expected to conclude roughly 7 billion years from today, resulting in the formation of a single, colossal, elliptical galaxy, a massive, unstructured collection of stars. This future cosmic entity has already been given a name by astronomers, Milcom, or sometimes Milkdromeda. However, a layer of complexity has been added to this forecast by more recent investigations. A 2025 study, which utilized data from the Gaia spacecraft and the Hubble telescope, revealed a different potential outcome. When the gravitational pull of the Large Magellanic Cloud and the Triangulum Galaxy are factored into the models, the likelihood of a direct collision decreases to about 50%. This introduces a significant possibility that the two galaxies might instead swing past one another, never fully merging within the next 10 billion years. This represents the current frontier of our scientific knowledge on the matter. The collision is no longer a certainty, and its timeline is now ambiguous. What remains definite is that the Milky Way and Andromeda are gravitationally intertwined. Their immense halos are already making contact. We are, in effect, witnessing the very early phases of one of the most momentous cosmic events in the history of our local group. Whether this collision unfolds in 4 billion years, 10 billion years, or perhaps not at all, a fundamental truth persists. Andromeda is moving toward us, and we are moving toward it. The question of what will happen when they finally meet remains. The timeline itself feels almost incomprehensibly vast. 4 billion years is a difficult span of time to grasp. To offer some perspective, 4 billion years in the past, Earth was a desolate, barren world. There were no plants, no animals, and not even the single-celled organisms we recognize today. The very first bacteria were only just starting to emerge in the primordial oceans. The entirety of what has transpired since all of biological evolution and all of human history occupies a shorter period than the time that still separates us from this potential collision. 4 billion years into the future, our planet will be unrecognizable, assuming it continues to exist at all. The most immediate threat to Earth is not the distant galactic merger, but rather our own star. Over the coming billions of years, the Sun is set to gradually increase its luminosity. This is a natural part of stellar aging. As hydrogen fuses into helium within its core, the resulting helium ash builds up, which in turn increases the core's density and temperature. This process accelerates the fusion reactions, causing the star to release more energy. In about 1 billion years, our sun will shine approximately 10% brighter than it does now. While that might not seem like a dramatic change, it would be sufficient to initiate a runaway greenhouse effect on Earth. The planet's oceans would start to boil away. Because water vapor is an extremely potent greenhouse gas, it would trap more heat, leading to more evaporation in a powerful feedback loop. In just a few 100 million years, Earth would come to resemble Venus, a torched, sterile planet where surface temperatures are high enough to melt lead. By the time Andromeda and the Milky Way might actually collide, our sun will be somewhere between 35 and 40% brighter than it is today. Life on Earth would have long since vanished. The habitable zone, which is the orbital region around a star where liquid water can persist, will have shifted much farther out. It's conceivable that Mars or even the moons of Jupiter could become habitable by then. Alternatively, life might have already found a new home in a different star system. If humanity or its descendants are still around, they would have a privileged view of the most breathtaking cosmic display imaginable. The night sky would be utterly transformed. Andromeda would dominate the view from horizon to horizon, a brilliant, swirling tapestry of billions of stars. The two galaxies would then begin to interpenetrate, their vast disks passing through each other almost like phantoms. It's important to note that individual stars themselves will not collide. The sheer emptiness of space makes such events exceedingly rare. The average distance separating stars is several light years. A galaxy is fundamentally empty space, punctuated by sparse points of light. The gas, however, is another story. When immense clouds of hydrogen and helium crash into one another at speeds of hundreds of miles per second, they become compressed and heated. This compression triggers furious bursts of star formation. Computer simulations suggest that millions of new stars will ignite during the merger, bathing the newly formed galaxy in a brilliant blue light. Stellar nurseries would spring up throughout the structure. Giant molecular clouds, some spanning hundreds of light years, would collapse to form dense clusters of hot, young stars. These newborn stars would be ephemeral. The most massive among them would detonate as supernovae after only a few million years, seeding the surrounding gas with heavy elements and sparking subsequent waves of star birth. Our own sun is very likely to survive this galactic encounter without any harm. The probability of a direct stellar impact is almost infinitesimally small. What will change, however, is our sun's orbit around the galactic center. At present, our solar system is located about 26,000 light-years from the Milky Way's core, moving at a relatively calm speed of around 140 miles per second. After the merger, simulations indicate we could be propelled much farther out, perhaps to a distance of 50,000 light-years from the new galactic nucleus. There is also a small but non-zero chance, calculated at roughly 12%, that our solar system could be ejected from the merged galaxy entirely. Gravitational interactions during the collision could impart enough velocity to our sun for it to escape the galaxy's pull altogether. We would become an intergalactic wanderer, drifting through the void between galaxies with no home disk. The most spectacular event, however, would unfold at the very heart of the new galaxy. The two supermassive black holes, one from each of the original galaxies, would begin a long, spiraling dance toward each other that would last for millions of years. When they finally merge, they will unleash a torrent of gravitational waves, with enough power to be detected by advanced civilizations thousands of galaxies away. That climactic collision is still billions of years in our future, or perhaps, given the recent data, it is not. When two supermassive black holes collide, the very structure of reality trembles. The fabric of space-time ripples outward as waves of gravitational energy, propagating across the cosmos at the speed of light. This is not a concept from science fiction. It is confirmed physics, first predicted by Einstein more than a century ago, and later directly observed by the LIGO and Virgo detectors in 2015. The black hole at the center of the Milky Way has a mass equivalent to about 4 million times that of our Sunday Andromeda's. Central black hole is far larger, weighing in at 140 million solar masses. When these two cosmic behemoths finally coalesce, their merger will, for a fleeting moment, release more energy than all the stars in the observable universe combined. But reaching that final moment is a very long process. Black holes do not simply crash into one another. The two supermassive black holes are destined to orbit one another, their paths slowly decaying as they shed energy in the form of gravitational waves. This is a process that can unfold over hundreds of millions of years, its duration dictated by their initial distance and orbital speeds. When the parent galaxies first encounter each other, their central black holes will be separated by tens of thousands of light years. From there, they will embark on a long, deliberate journey toward the center of the newly merged galaxy. This initial phase is governed by a phenomenon known as dynamical friction, where the gravitational drag from countless passing stars and vast gas clouds systematically saps the black holes of their orbital energy. With every pass, their orbits shrink, bringing them inexorably closer. A critical transition occurs when their separation dwindles to just a few light years. At this point, the emission of gravitational waves becomes the dominant force shaping their fate. The black holes begin to radiate their energy away as ripples in space-time, which causes their orbit to decay at a rapidly accelerating rate. They spiral toward each other faster and faster, eventually whipping around one another at a significant percentage of the speed of light. In the final seconds before they coalesce, the two behemoths will be orbiting each other hundreds of times per second. The powerful gravitational waves they generate will possess frequencies that fall squarely within the detection range of future space-based observatories. It is a quiet thought that if humanity still exists and continues to build such instruments, this merger would be the single greatest astronomical event of the millennium. The collision itself is astonishingly brief, lasting for only a fraction of a second. The two event horizons will touch and then fuse, forming a single, larger black hole. The merger, however, is anything but a clean event. The newly combined black hole will be spinning violently and will be highly distorted from a perfect sphere. It will proceed to ring like a struck bell, oscillating as it sheds these deformities and settles into a stable configuration. This ring-down phase broadcasts a final, distinct burst of gravitational waves before the black hole once again falls silent. Its final mass will be approximately 144 million times that of our Sun, which is the simple sum of its two progenitors. A fascinating detail, however, is that a small fraction of their mass, perhaps between 1 and 5%, will be converted directly into pure energy in the form of these gravitational waves. This immense release of energy radiates outward at the speed of light, carrying with it precise information about the masses, spins, and orbital characteristics of the merging pair. If the two original black holes possess different spins, the merger can result in a powerful recoil kick. This could eject the newly formed black hole from the galactic center entirely, sending it hurtling away at speeds of hundreds or even thousands of miles per second. This is not mere speculation. It is a real phenomenon, predicted by detailed simulations, and has possibly been observed in a handful of other galaxies. Should this occur during the Milky Way and Andromeda merger, the resulting galaxy would be left without a central black hole for millions of years, at least until the ejected object eventually falls back toward the core. The stars in the immediate vicinity of the merger will be profoundly affected. As the black holes spiral together, their immense gravity will scatter nearby stars, flinging them away in random directions. Some stars will be accelerated to escape velocity, launched out of the galaxy to become lonely wanderers in intergalactic space. Others will be captured into tight, perilous orbits around the new, larger black hole, their ultimate fate being tidal disruption. The surrounding gas will be similarly disrupted. Any gas that had been orbiting either of the original black holes will be violently stirred up by the merger. This turbulence could trigger a massive burst of accretion onto the newly formed black hole, causing it to light up as an active galactic nucleus. For a period of a few million years, the center of this new galaxy, Milkomeda, might shine with the intensity of a quasar, far outshining the combined light of all its trillions of stars. This is the destiny that awaits the very hearts of the Milky Way and Andromeda. Two black holes, each born from the deaths of countless stars, will combine into a single cosmic monster at the core of a new galaxy. But before that can happen, an even more chaotic event must first take place: the collision of the galaxies themselves. The name astronomers have coined for this future galaxy, Milkomeda, is a whimsical portmanteau of Milky Way and Andromeda. Yet there is nothing whimsical about the cosmic process that will bring it into existence. When two spiral galaxies merge, the final outcome is determined by several factors, including the mass ratio between them, the amount of gas left in their disks, and the specific angle and speed of their collision. In the case of the Milky Way and Andromeda, simulations consistently predict that the result will be a giant elliptical galaxy. Elliptical galaxies bear little resemblance to the spirals we know. They lack a distinct disk, have no beautiful spiral arms, and exhibit no organized rotation. Instead, they are vast, bloated, football-shaped clouds of stars, all moving on random orbits. Most stars within an elliptical galaxy follow chaotic paths that repeatedly carry them through the galactic center. The overall structure is smooth and largely featureless, missing the intricate, delicate beauty of a spiral. The reason mergers tend to produce ellipticals is that the collision itself destroys the organized rotation of the two original spiral galaxies. The gravitational interactions fling stars in all directions, scrambling the orderly orbits that once defined the spiral arms. By the time the merger is complete, the stars are moving on random trajectories, creating the spherical or ellipsoidal shape that is characteristic of these galaxies. Milkomeda is projected to be an immense structure. When including dark matter, the combined mass of the Milky Way and Andromeda will be close to 2 trillion solar masses. In terms of visible stars alone, Milkomeda will contain roughly 1.3 trillion stars, making it one of the most massive galaxies in our local group. Its central bulge will be enormous. Both our galaxy and Andromeda possess substantial bulges, which are dense concentrations of old stars at their cores. When these galaxies merge, their bulges will combine, creating a superbulge that will dominate the inner region of Milkomeda. During the merger, star formation will experience a dramatic spike, only to decline just as rapidly afterward. As gas clouds from the two galaxies collide, they will be compressed and fragmented, triggering intense bursts of new star formation. Simulations suggest that millions of massive stars will be born over a span of a few 100 million years. These stars will be hot and blue, temporarily giving Milkomeda a bluish hue. This period of prolific star birth, however, cannot last. Galactic mergers are highly efficient at consuming available gas. The collision will funnel gas toward the galactic center, where some of it will form stars, and some will be consumed by the central black hole. Any remaining gas will be heated to temperatures so high that it can no longer collapse to form new stars. Within 1 billion years after the merger is complete, Milkomeda will have used up most of its star-forming fuel. This means the new galaxy will age quickly. With no new stars being born, it will gradually redden as its massive blue stars burn out and die, leaving behind only the long-lived, smaller red stars. In 10 billion years, Milkomeda will be what astronomers call a red and dead elliptical, a galaxy composed almost entirely of old, low-mass stars that will slowly fade over the coming trillions of years. The final size of Milkomeda is somewhat harder to predict, as elliptical galaxies tend to be puffier and more diffuse than their spiral predecessors. When the orbits of stars are thoroughly scrambled, they begin to spread apart, giving rise to a much larger cosmic structure. The resulting galaxy, which has been named Milkomeda, could span a diameter of more than 200,000 light-years, making it more expansive than either of its two parent galaxies. Yet Milky is not destined to form in isolation. The Triangulum galaxy, which is the third largest member of our local group, will almost certainly be drawn into the merger as well. Triangulum is a relatively small spiral galaxy, measuring about 60,000 light-years across. It currently follows a distant orbit around Andromeda, but the powerful gravitational forces at play during the main collision are expected to pull Triangulum into the event. Should this occur, Milky will then absorb Triangulum, becoming even more massive in the process. What follows is a slow, inexorable gathering. Over the next 150 billion years, every other galaxy remaining in the local group will eventually fall into Milky. This includes dozens of dwarf galaxies and any leftover satellite systems. Everything that is gravitationally bound to the local group will ultimately combine into a single, giant elliptical galaxy. This represents the long-term future of our cosmic neighborhood. It is a future not of stars scattered among many galaxies, but of one solitary island of light, surrounded by the ever-expanding void of intergalactic space. And somewhere within that immense galaxy, orbiting far from its brilliant core, there might still be a yellow star that was once our home. However, its survival within the new galaxy is not guaranteed, as not every star will successfully make the transition into Milky. When galaxies collide, the resulting gravitational chaos can fling some stars out of the system entirely. These stars become what are known as hypervelocity stars, cosmic orphans destined to travel through the intergalactic void with no home galaxy to anchor them. The existence of hypervelocity stars is not theoretical, they are a known reality. Astronomers have already identified dozens of them within our own Milky Way. These are stars moving at speeds that exceed 370 miles per second. A velocity this high is more than sufficient for a star to break free from the galaxy's gravitational pull forever. It is believed that most of these stars were likely ejected through gravitational encounters with the supermassive black hole at the galactic center. A common scenario involves a binary star system wandering too close to the black hole. As one star is captured into an orbit, its companion is violently flung outward at an incredible speed. During the merger of the Milky Way and Andromeda, this very process will unfold on a truly massive scale. Simulations of the collision predict that a substantial portion of the stars from both galaxies, somewhere between 10 and 20%, could be ejected into the vastness of intergalactic space. This translates to hundreds of billions of stars being cast out into the void. Imagine for a moment what it would be like to live on a planet that orbits one of these ejected stars. You would grow up under a sky dominated by the bright, sprawling disk of your home galaxy, a luminous spiral stretching from horizon to horizon. Then, over the course of a few million years, you would witness that familiar disk begin to recede. The galaxy would appear to shrink, growing progressively smaller and dimmer as your own star accelerated away from it. Within just 10 million years, your home galaxy would be little more than a bright smudge in the distant sky. After 100 million years, it would have faded to a faint patch of light, nearly impossible to distinguish from the countless other galaxies scattered across the cosmos. Your star would be truly alone, drifting through the profound darkness between galaxies, with its nearest neighbors millions of light-years away. The night sky from such a world would be almost entirely black. There would be no Milky Way arching overhead and no brilliant galactic core. There would only be a sparse scattering of distant galaxies, each one a faint, fuzzy blob. And perhaps, if you were fortunate enough to be part of a small ejected group, a few hundred stars from your own former cluster. This fate, however, is not a certainty for every star. The majority of stars will remain gravitationally bound to Milky. The ones most at risk are those located near the outer edges of the galaxies at the time of the collision. Gravitational slingshot effects will accelerate these stars beyond their escape velocity, condemning them to a future of eternal isolation. Some of these hypervelocity stars will be moving so rapidly that they escape the pull of the local group entirely. They will journey across the tens of millions of light-years that separate our local group from neighboring galaxy clusters. In a few billion years, some of them might find themselves falling into the Virgo cluster, where they would be captured by the gravity of a completely different galactic collective. Others will remain bound to the local group, but will exist outside the main body of Milkomeda. They are destined to orbit the newly merged galaxy at enormous distances, creating an extended, sparse halo of isolated stars. Over trillions of years, a few of these might eventually fall back toward Milkomeda. Others will remain in the outer darkness forever. The process of ejection is not entirely random. A star's location plays a crucial role. Stars in the outer regions of each galaxy are far more likely to be flung away. In contrast, stars within the dense central bulges have a much higher probability of remaining bound to the new structure. This dynamic helps to explain why elliptical galaxies like Milkomeda often have lower mass halos than the spiral galaxies that formed them. The collision effectively strips away the outer stars, leaving behind only the tightly bound core. Our own solar system happens to be situated in the outer disk of the Milky Way. Consequently, we are not in the most secure location. Simulations of the merger give our system roughly a 12% chance of being ejected entirely. While this is not a high probability, it is far from negligible. A real possibility exists that when the collision finally happens, our star will be thrown into the lonely expanse of intergalactic space. If that were to occur, any future inhabitants of Earth, assuming any still exist, would witness their home galaxy receding into the distance over millions of years. They would become true cosmic nomads, wandering the great void between the galaxies. But there is another possibility, an outcome that is considerably more likely. Our star might remain bound to Milkomeda, but its orbit could be altered in a dramatic fashion. The question then becomes, where in this new galaxy would we end up? At present, our star follows an orbit around the Milky Way at a distance of approximately 26,000 light-years from the galactic center. We complete a single orbit once every 230 million years. The last time our solar system was on the opposite side of the galaxy, dinosaurs still walked the Earth. This orbit is stable and predictable, and it has remained essentially unchanged for billions of years. That long period of stability is now destined to end. When the Milky Way collides with Andromeda, every single star in both galaxies will experience a violent disruption of its orbit. Gravitational interactions will toss stars in random directions, completely scrambling the orderly, rotating disks of the two spirals. Our star will not be immune to this chaos. Simulations provide a clear picture of the most probable outcome for our solar system. Our star is likely to be kicked outward, pushed to a new distance of roughly 50,000 light-years from the center of Milkomeda. This is nearly double our current distance from the Milky Way's core. We would become outer halo stars, orbiting far from the bright central bulge where the majority of Milkomeda's stars will eventually congregate. The view from Earth, if our planet still exists, would be profoundly different. Currently, the Milky Way's disk appears as a brilliant band of light stretching across our night sky. From our new location in Milkomeda's outer halo, the galactic disk would no longer surround us. Instead, we would gaze upon the entire galaxy as a distant, glowing sphere. Its central bulge would be the most prominent feature, a concentrated ball of old red stars that would dominate the view. As a result, the night sky would become much darker overall. From our new position, farther from the galaxy's most populated stellar regions, fewer stars will be visible to the unaided eye. The appearance of our home galaxy will shift, looking less like the familiar Milky Way and more like a remote elliptical galaxy, though one of extraordinary brightness since we will still be inside it. Our solar system's orbital velocity will also be different. In the outer halos of elliptical galaxies, stars tend to follow highly eccentric orbits. Instead of a stable, circular course, our Sun might be pulled into an elongated ellipse, a path that would carry it near the galactic core before swinging it far back out into the halo. These plunging orbits can take hundreds of millions of years to complete one cycle. A 12% chance also exists that our solar system could be ejected from the galaxy altogether. As noted before, should this happen, we would become an intergalactic wanderer. Our star would depart Milky entirely, set adrift in the cosmic void with no galaxy to call home. The night sky would become almost completely dark, punctuated only by the faint light of distant galaxies. But here is the essential takeaway. None of this will impact the habitability of Earth. The collision of galaxies is a process that plays out over scales of thousands of light years. Our star's immediate neighborhood, the area spanning a few light years around us, will be entirely undisturbed. The planets will maintain their orbits just as they do today. The asteroid belt will hold its stable configuration. The Oort cloud will remain gravitationally tethered to the outer solar system. Individual stars are not going to collide. The expanses between stars are simply too vast for this to occur. Even within the most crowded parts of the galactic core, stars are separated by light years. The probability of a direct stellar collision during the merger is less than 1 in a trillion. There is, however, a small risk associated with a near pass. If another star were to travel within a few light years of our solar system, its gravitational influence could disrupt the Oort cloud, sending a cascade of comets into the inner solar system. Such an event could unleash a bombardment similar to the late heavy bombardment that Earth witnessed 4 billion years ago. For any life on Earth at that time, the consequences would be catastrophic. The likelihood of this happening is low, probably under 1%. In all probability, our star will simply be guided to a new orbit within Milky without any such close encounters. Our planetary system will stay completely intact. The only real changes will be our location within the galaxy and the panorama of the night sky. This all, of course, presumes that Earth remains a habitable world when the collision takes place. As previously mentioned, our Sun's increasing luminosity is expected to make Earth uninhabitable in about 1 billion years, well before the galaxies complete their merger. Any life form that bears witness to the collision will likely be inhabiting a different planet or will have already relocated to an entirely new star system. The specifics of our star's fate are uncertain, but the general outline is quite clear. We will survive the galactic merger. We will be shifted to a new orbit, and we will spend the remainder of our existence as residents of Milky, the giant elliptical galaxy created from the union of our two cosmic homes. Yet, something happening right now at the heart of Andromeda suggests this collision could be more violent than anyone anticipated. The Chandra X-ray Observatory has been observing Andromeda's core for more than 2 decades. The universe's most extreme processes are revealed through X-rays, such as superheated gas, matter spiraling into black holes, and colliding neutron stars. Chandra can see what optical telescopes cannot: the high-energy chaos hidden within galactic centers. For years, Andromeda's central black hole gave off a faint, consistent X-ray signal. This baseline emission originated from hot gas in its immediate surroundings, where material was heated to millions of degrees by friction and magnetic fields. This was entirely expected, as even quiescent black holes emit some X-rays from their accretion zones. Then, the flares started. In 2006, the X-ray brightness suddenly intensified, jumping by a factor of 100 inches a matter of hours. The black hole was effectively screaming in X-rays, bathing its environment in high-energy radiation. This flare persisted for several days before it subsided to the baseline level. Astronomers found it interesting but not alarming, since black holes can have occasional outbursts when they consume large clumps of gas. 7 years later, it happened once more. Another huge X-ray flare erupted from the core, this one even more powerful than the first. The timing appeared to be random. with no clear trigger or visible disruption in the nearby gas. The black hole just erupted without any warning. Ever since, the baseline X-ray emission has stayed at this higher level. The black hole has not returned to its former quiet state. It continues to generate X-rays at a greater rate than it did prior to 2006. The flares have also continued, with smaller outbursts occurring every few years. A recent analysis published in 2025 looked at 15 years of Chandra data. This study confirmed what many astronomers had begun to suspect. The black hole has entered a new phase of activity. Something fundamental changed around the year 2006. While the precise cause is still unknown, the pattern is unmistakable. X-ray flares of this intensity are indicative of violent accretion events. Material that falls toward a black hole does not descend in a smooth flow. It spirals inward, heating up as it progresses. When an especially dense clump of gas arrives at the inner accretion disk, it can set off a sudden discharge of energy. The gas is compressed, heated to incredible temperatures, and lets out a burst of X-rays just before it crosses the event horizon. But there is an alternative possibility. The flares could be connected to magnetic field reconnection. In the chaotic environment near a black hole, magnetic fields can become twisted and tangled. When these field lines suddenly snap and reconnect, they unleash tremendous amounts of energy in seconds. The process is analogous to solar flares on our own star, but it is billions of times more powerful. The hardness of the X-rays offers clues. Hard X-rays possess higher energies than soft X-rays. By measuring the ratio of hard to soft X-rays, astronomers can infer the temperature and density of the gas emitting them. Andromeda's flares produce what are considered relatively soft X-rays compared to the flares from the Milky Way's black hole. This points to different physical conditions in the two accretion zones. The link between these X-ray flares and the black hole's overall activity level is significant. If its feeding rate were increasing, we would expect to see more frequent and more powerful flares. That is precisely what the data indicates. The black hole is consuming more material than it was 20 years ago. This discovery has profound implications. If Andromeda's black hole is indeed transitioning from a dormant to an active state, the core of that galaxy is set to transform over the next few million years. When a black hole is active, it can produce what are known as jets, which are immense columns of particles and radiation. These jets are expelled from the polar regions at velocities approaching the speed of light. Their reach is extraordinary, capable of extending for hundreds of thousands of light years, pushing far past the boundaries of their host galaxy. As of now, no such jets have been observed emanating from the core of Andromeda. However, should the rate of accretion continue to climb, it is possible that jets could eventually take shape. In the distant future, when the Milky Way and Andromeda galaxies inevitably merge, the presence of an active black hole would make the collision significantly more energetic than current simulations suggest. The recently detected X-rays can be seen as a quiet signal. The central black hole appears to be stirring from a long slumber. Its next actions could potentially reshape the destiny of the entire galaxy. Yet, these X-rays are not the only unusual transmissions originating from Andromeda's core. There is another, more structural mystery. We have confirmed the existence of 14 satellite galaxies in orbit around Andromeda. It is highly probable that more remain hidden, yet to be discovered in the vastness of space. What astronomers find particularly puzzling, however, is the specific arrangement of these satellites. They are not orbiting in a random fashion. Instead, they travel together in a remarkably coherent structure, forming a thin, rotating plane that scientists have named the Great Plain of Andromeda. According to our current understanding of the universe, this formation should not exist. The standard cosmological models predict a different outcome. When smaller galaxies are captured by the gravitational field of a much larger one, they are expected to approach from all directions randomly. Over the course of billions of years, their orbits should become scattered, eventually forming a diffuse, spherical halo around the host galaxy. This is the result consistently produced by dark matter simulations. Andromeda's satellites, however, are in direct defiance of these well-established predictions. At least half of them are confined to a plane that is merely 13,000 light-years thick, yet it stretches out over a distance of hundreds of thousands of light-years. What is more, the plane itself is in rotation, with the satellites all moving in the same general direction, much like planets orbiting a star. The degree of this organization is so high that it is considered statistically improbable. This discovery was the result of meticulous measurements of the satellite galaxies' velocities, conducted with ground-based telescopes. As astronomers mapped out the three-dimensional positions and movements of these small galaxies, the planar structure became unmistakably clear. It seems impossible for it to be a mere coincidence. Some underlying force or event must have created this peculiar arrangement. Several theories have been proposed to explain this phenomenon. One idea suggests that the satellites are the surviving fragments of a much larger structure that fell into Andromeda as a single group. It is conceivable that a filament of galaxies, a kind of cosmic highway of matter that links larger galaxy clusters, passed near Andromeda billions of years ago. As this filament met Andromeda's immense gravity, it would have been torn apart, leaving behind a trail of smaller galaxies all traveling along a similar path. An alternative theory involves the tidal forces exerted by our own Milky Way galaxy. The gravitational influence from our galaxy could be subtly stretching Andromeda's satellite system. This stretching might cause the satellites to settle into certain preferential orbits over others. Computer models have shown that such a process could indeed form a planar structure over billions of years. But both of these theories face significant challenges. The plane is remarkably thin and has remained stable for a very long time. Gravitational interactions with Andromeda and other galaxies should have disrupted it by now. The satellites ought to have been scattered into more randomized orbits. And yet, the plane endures. This persistence hints at a more unsettling possibility. Perhaps our fundamental understanding of dark matter is incomplete. Dark matter remains invisible to us, its presence inferred only through its gravitational pull on visible matter. We know it must exist because galaxies rotate at speeds too great to be held together by their luminous matter alone. We also know that it outweighs normal matter by a ratio of approximately 6:1, but we still do not know what it is composed of. If dark matter possesses properties that we have not yet discovered, it might be capable of forming structures that our standard models do not account for. It could be that under specific conditions, dark matter can organize itself into disks or planes. Perhaps Andromeda's dark matter halo is not spherical as is typically assumed, but is instead flattened. Such a shape could naturally guide satellite galaxies into these preferred orbital paths. This remains in the realm of speculation, not confirmed science. But the great plane of Andromeda is not speculation. It is a confirmed observational fact. Something brought this structure into being, and our current models find it very difficult to explain. The James Webb Space Telescope is now providing new insights that are helping to refine our comprehension. It is studying individual stars within some of these satellite galaxies. By carefully measuring their ages and chemical compositions, astronomers can begin to piece together when and where these small galaxies originally formed. If it turns out they all came into being at the same time and from the same primordial material, this would lend strong support to the filament theory. If, however, they have diverse and unrelated histories, the mystery will only become more profound. A closer look reveals that some satellites within the plane are currently being torn apart. Long stellar streams can be seen extending from them. This is clear evidence of tidal disruption. These streams represent the final moments of these small galaxies, their death throes before they are completely absorbed into Andromeda's vast halo. The satellites that exist outside the plane exhibit different traits. They are generally smaller, older, and have a lower concentration of heavy elements. These likely fell into Andromeda's gravitational well much earlier. and have had billions of years to scatter into the random orbits that theory predict. This suggests the satellites in the plane are comparative newcomers. They were captured more recently and still retain some of the coherence from their initial trajectory. Regardless of its origin, the Great Plain of Andromeda has a finite existence. Over the next several billion years, gravitational forces will inevitably scatter the satellites. The plane will gradually thicken and, in time, dissolve completely. And when the Milky Way finally collides with Andromeda, any satellites that remain will be thrown in all directions by the sheer chaos of the merger. But for now, this ring of dwarf galaxies continues its eerie, synchronized orbit. It is a structure that should not exist, encircling a galaxy that is slowly preparing to consume it. And just beneath that strange ring, hidden structures are glowing in wavelengths that only the Webb telescope can perceive. Dust can be thought of as the skeleton of a galaxy. It traces the elegant spiral arms, it outlines the active regions of star formation, and it conceals the most violent processes that occur deep within the galactic core. Visible light is unable to penetrate these thick veils of dust. It is scattered and absorbed, which renders entire sections of a galaxy invisible to optical telescopes like Hubble. Infrared light, however, can pass through dust almost as if it were not there, like a ghost moving through walls. When the James Webb Space Telescope turned its gaze to Andromeda in mid-infrared wavelengths, it unveiled structures that had been hidden from view for billions of years. It saw dust rings encircling the galactic center, glowing with the gentle heat of the stars embedded within them and from warm molecular clouds. These rings are not perfectly uniform. They show gaps, clumps, and various distortions, all of which tell a story of recent and violent events. The innermost ring is situated approximately 3,000 light-years from the central black hole. It is a dense region, filled with cool stars and complex organic molecules. The dust grains that make up this ring are intricate, containing compounds of carbon, silicon, and iron that were forged in the atmospheres of dying stars. Webb spectroscopic instruments are sensitive enough to identify these specific compounds by their unique infrared signatures. Temperature readings from the ring show that it is warmer than expected, indicating that something within it is providing an additional source of heat. The most likely explanation for this glow points to recent star formation. When massive stars are born, they bathe their local environment in powerful ultraviolet radiation. This intense light heats the surrounding dust, which then begins to glow brightly in the infrared. But there is another source of heat to consider, and that is the galaxy's central black hole itself. Although it is not currently feeding at a high rate, any material that does fall into its grasp releases a vast amount of energy. This energy warms the nearby gas and dust. The result is a warm zone that permeates the innermost few thousand light-years of the galaxy. The Webb telescope can measure this heat gradient with great precision, tracking exactly how the temperature falls as one moves away from the center. A second ring is situated much farther out, at a distance of roughly 10,000 light-years from the galactic core. This outer structure is cooler and appears more fragmented. It seems to be the lasting evidence of a spiral arm that was disrupted during a merger in the distant past. When Andromeda absorbed a smaller galaxy a few billion years ago, the collision sent powerful shockwaves through the disk. These waves compressed vast clouds of gas and triggered intense bursts of star formation. The dust ring we see today is what remains of that ancient event. Webb's observations of this outer ring revealed something entirely unexpected. The data showed an unusually high abundance of polycyclic aromatic hydrocarbons. These are complex organic molecules containing carbon and hydrogen arranged in distinctive hexagonal patterns. While such molecules are common in space and are found in interstellar clouds throughout the universe, their concentration in Andromeda's dust ring is remarkably high. These molecules are forged in the atmospheres of carbon-rich stars. When these stars die and shed their outer layers, they release these organic compounds into the interstellar medium. The molecules themselves are incredibly tough, surviving the harsh radiation of the galaxy for millions of years. They also play a crucial role in the chemistry that takes place within star-forming regions. The gaps within the dust rings are equally interesting. Something has clearly carved channels through the dust, creating zones that are relatively empty. One possibility is that stellar winds from massive stars are responsible. Hot, luminous stars produce powerful stellar winds that can blow away nearby gas and dust, creating vast bubbles and cavities. Over millions of years, these bubbles can expand to hundreds of light years across. Another possibility is that jets from the central black hole carved these gaps. Even a weakly active black hole can produce narrow jets of high-speed particles. If such jets have been intermittently active over the past few million years, they could have cleared these channels through the dust rings. The clumps seen in the rings suggest that star formation is still an ongoing process. When a dense clump of gas collapses, it typically fragments into multiple protostars. These young stellar objects are still embedded deep within their natal cocoons of dust. They are invisible light, but they shine brightly in the infrared. Webb can see them clearly, allowing astronomers to count how many stars are currently forming in Andromeda's core. The data shows that star formation is indeed happening, but at a modest rate. Andromeda creates fewer stars per year than the Milky Way, despite being the more massive galaxy. This observation confirms the theory that Andromeda used up much of its star-forming gas during past mergers. The dust rings, however, hold another secret. They are moving, rotating around the galactic center at speeds measured by comparing observations taken years apart. This rotation reveals the distribution of mass in Andromeda's core, which in turn helps astronomers map the invisible dark matter halo. The dust is not just simple debris, it is a crucial component of the galactic ecology. It absorbs ultraviolet light from young stars and re-emits that energy as infrared light. It provides surfaces where molecules can form. It also shields delicate star-forming regions from destructive radiation. Without dust, galaxies would look very different. What Webb sees in Andromeda's dust rings suggests something is actively disturbing them. The clumps are distributed asymmetrically. The temperature gradients are uneven. Some force is stirring up the material in the core. In specific regions, star formation appears to be accelerating. New stars are being born in Andromeda right now. They are not forming in vast numbers, but rather in specific pockets where conditions have become just right. These are places where gas clouds have been compressed beyond a critical threshold. Temperatures are low enough for hydrogen to clump together, and densities are high enough for gravity to overcome internal pressure. When all these factors align, stars ignite. The James Webb Space Telescope has mapped these star-forming regions with unprecedented precision. By observing in near-infrared wavelengths, Webb can peer into the dusty cocoons where protostars are gestating. These young stellar objects are still accumulating mass from their surrounding disks. They are not yet hot enough to ignite full hydrogen fusion, but they are warm. They emit a glow in infrared light that penetrates the very dust enshrouding them. Andromeda has several major star-forming complexes. The most active sits in the northern spiral arm, roughly 40,000 light-years from the galactic center. This region contains massive molecular clouds that span hundreds of light-years. They are dense enough to birth thousands of stars over the next few million years. Webb's images reveal the internal structure of these clouds in stunning detail. We can see filaments of dense gas threading through the cloud, and cores where the gas has already collapsed into protostars. We can also see outflows where young stars are blasting jets of material into space, clearing their surroundings. The level of detail is extraordinary. In the nearest regions, individual forming solar systems can be resolved. What surprises astronomers, however, is that this star formation is not where they expected to find it. Standard models predicted the most intense star formation should occur in the densest parts of Andromeda's disk, where gas is most abundant. Instead, Webb found active star formation in regions that appeared relatively quiet in visible light observations. These hidden nurseries exist because they are wrapped in thick dust. To Hubble, they appeared as dark patches, regions where starlight was simply blocked. Webb sees through the dust and reveals the birth chambers of new stars. The temperature of the dust provides crucial information. Hot dust indicates the presence of nearby young stars. Cool dust, on the other hand, suggests older, more evolved regions. Chemical analysis through spectroscopy reveals what elements these new stars will contain. Gas clouds in Andromeda are metal-rich compared to the Milky Way. This means they contain higher abundances of elements heavier than hydrogen and helium. This is because Andromeda has experienced more supernova enrichment over its history. Each generation of massive stars that lived and died added more heavy elements to the galactic gas reservoir. The rate of star formation in Andromeda is roughly 2 to 3 stellar masses per year. This means that every year, enough gas collapses to create 2 or 3 stars with a mass comparable to our own Sunday. Andromeda's rate of star birth is more measured than that of the Milky Way, which generates roughly 7 new stars annually. This difference in pace is quite revealing. The Andromeda Galaxy possesses less available gas for this process, as much of it was used up or ejected during previous galactic mergers. Even so, certain regions within Andromeda display vibrant bursts of elevated star formation. These localized pockets of activity align with areas where Andromeda's smaller satellite galaxies have journeyed through its main disk. When a dwarf galaxy makes a passage through the gas-laden disk of a larger one, its gravity compresses the gas, setting off a chain reaction of star creation in its path. This phenomenon is supported by observations that show clusters of young stars tracing the orbital paths of several of these satellite galaxies. The Webb telescope also identified pre-stellar cores, which are dense clumps of gas that have not yet ignited into stars but are poised to do so. These cores are incredibly cold, hovering at just 10 to 20 degrees above absolute zero. Their structures are delicate, held together by only the faintest pull of gravity. The slightest disturbance could either initiate their collapse or scatter them completely. The most massive of these protostars are destined to become blue giants, stars that possess tens of times the mass of our Sunday. Their lives will be brilliant but brief, culminating in supernova explosions after only a few million years. Through their explosive deaths, they will enrich the galaxy with heavy elements, providing the material for the next generation of stars and planets. In contrast, the smallest protostars will evolve into red dwarfs. These are stars that will continue to burn for trillions of years. They will still be glowing long after Andromeda and the Milky Way have merged to form Milkdromeda, and long after the vast majority of other stars have extinguished. The map of star-forming zones created by Webb offers a detailed snapshot of Andromeda's present activity. The galaxy is far from dormant. It continues to actively forge new stars, though at a more subdued rate than it did in its earlier eons. When the eventual collision with the Milky Way takes place, this entire process will intensify dramatically. Vast clouds of gas from both galaxies will collide and become compressed, igniting the most powerful burst of star formation Andromeda has seen in billions of years. But these gas clouds are composed of more than simple hydrogen. They function as cosmic chemical factories, manufacturing an array of complex molecules. What the Webb telescope discovered floating within those clouds is truly remarkable. The space between stars is not a perfect vacuum. It is filled with a tenuous soup of atoms, molecules, and fine dust grains. The primary component is hydrogen, the universe's simplest and most plentiful element. Yet, sprinkled throughout this medium are more exotic compounds, such as carbon monoxide, water ice, methane, ammonia, and organic molecules that could, under the right circumstances, give rise to life. The James Webb Space Telescope is specifically designed to detect these very molecules. Its powerful infrared spectrometers can pinpoint specific chemical compounds by analyzing their unique signatures of absorption and emission. As light from a distant star travels through a molecular cloud, the molecules within it absorb very specific wavelengths. The resulting spectrum acts like a chemical barcode, revealing the exact composition of the cloud. Within Andromeda's molecular clouds, Webb uncovered a rich supply of carbon-based molecules, including the polycyclic aromatic hydrocarbons mentioned before, as well as simpler compounds like methane and ethane. These molecules are forged in the atmospheres of carbon-rich giant stars. As these stars age and shed their outer layers, they release these complex compounds into the interstellar medium. Methane is a particularly compelling discovery. Here on Earth, methane is overwhelmingly a product of biological activity, from bacteria in wetlands to the digestive processes of animals and the decay of organic material. While methane in space is formed through non-biological chemistry, its existence still points to complex chemical pathways at work. The molecular clouds in Andromeda are frigid, with temperatures of only 10 to 50 degrees above absolute zero. In such extreme cold, many molecules freeze onto the surfaces of dust grains, creating icy mantles. These frozen layers contain water, carbon monoxide, methane, and even more complex organic substances. When new stars begin to form out of these clouds, the heat causes these ices to sublimate back into gas, which then becomes part of the protoplanetary disks. From there, these materials are eventually incorporated into comets, asteroids, and newly forming planets. This process means that every solar system currently taking shape in Andromeda is being seeded with organic molecules. The fundamental building blocks of life are being distributed across the entire galaxy. Whether life actually emerges from these materials is another matter, a question that hinges on a multitude of other factors. The essential raw ingredients, however, are clearly present. Webb also registered emissions from carbon monoxide, a molecule that readily forms in space when carbon and oxygen atoms meet. Carbon monoxide is prevalent in star-forming regions because it can withstand the relatively warmer temperatures found there. It serves as an excellent tracer, enabling astronomers to map the distribution and movement of molecular clouds. By analyzing the Doppler shift in the carbon monoxide emissions, scientists can calculate how quickly the gas is moving. This data unveils the internal dynamics of the molecular clouds themselves. Some areas are in a state of collapse, drawn inward by their own gravity. Other sections are expanding, pushed outward by powerful stellar winds. Still others are in rotation, spinning around a central protostar. The chemical makeup of these clouds also provides insights into Andromeda's past. The presence of molecules containing heavy elements like nitrogen, oxygen, and sulfur indicates that multiple generations of stars must have lived and died. These stars enriched the galaxy with these elements through their supernova explosions. The abundance of such molecules is higher in Andromeda than in our own Milky Way, which lends support to the idea that Andromeda has experienced more intense periods of star formation and more violent mergers. Ammonia was also detected in several of these clouds. This molecule, composed of nitrogen and hydrogen, forms in cold, dense gas where nitrogen atoms can easily combine with the abundant hydrogen. Ammonia is a crucial ingredient in prebiotic chemistry. Laboratory experiments on Earth have demonstrated that when ammonia is mixed with other simple molecules and exposed to energy sources like ultraviolet light or electrical discharges, it can lead to the creation of amino acids, the foundational components of proteins. Does this imply that Andromeda could potentially host life? It is a possibility. The galaxy contains a staggering 1 trillion stars. Even if a minuscule fraction of those stars have planets, and an even smaller fraction of those planets are habitable, the sheer numbers are immense. There could be millions of worlds within Andromeda where the conditions are right for life as we understand it. However, this is a question we will likely never be able to answer with certainty. Andromeda is simply too far away. Even our most sophisticated telescopes are incapable of resolving individual planets orbiting stars in other galaxies. We can study the galaxy as a whole, charting its structure and measuring its composition, but the ultimate question of life there remains beyond our reach. What we can state confidently is that Andromeda's molecular clouds are chemically rich environments, teeming with the very substances that make life possible. These vast clouds contain the fundamental ingredients for complex chemistry, and potentially even the chemistry of life itself. They are continuously renewed by dying stars, participating in a cycle of matter that has unfolded over billions of years. These formations, however, are not static. They are being acted upon by powerful forces that originate in the galactic core, forces capable of blowing gas out of the galaxy entirely. We can think of galaxies as breathing organisms. They draw in gas from the space between galaxies and then expel that material back out in the form of powerful winds. This entire cycle serves to regulate the formation of stars, controlling the speed at which a galaxy is able to grow. In the absence of these winds, galaxies would likely burn through their gas reserves far too quickly, converting it all into stars and then dying young. The winds act as a release valve, slowing down the entire process. Andromeda possesses its own galactic winds, which appear as streams of hot gas flowing outward from its center. This gas is heated to millions of degrees and propelled to speeds of hundreds of miles per second. The energy driving these winds comes from two primary sources, supernovae and the activity of the central black hole. When a massive star explodes as a supernova, it unleashes a tremendous amount of energy. For a period of weeks, a single supernova can even outshine its entire host galaxy. But the majority of that energy is not released as light. It is kinetic energy, an explosive force that hurls the star's outer layers into space at thousands of miles per second. When many supernovae detonate in the same region over a span of a few million years, their combined energy creates what is known as a superbubble. The expanding shock waves from each individual explosion merge together, carving out a cavity hundreds of light years across that becomes filled with hot, low-density gas. This gas is highly pressurized. It expands outward, eventually breaking through the plane of the galactic disk and escaping into the halo. This phenomenon is known as a supernova-driven wind, and it occurs in all galaxies that are actively forming stars. The Milky Way has these winds, and so does Andromeda. Even small dwarf galaxies experience them, though in those smaller systems, the winds can be powerful enough to eject most of the galaxy's available gas, effectively shutting down star formation for good. But a second source contributes to galactic winds: active black holes. When a supermassive black hole is feeding, it does not actually consume all of the material that falls toward it. A portion of that matter is instead accelerated and ejected in powerful jets or wide-angle winds. These outflows, driven by black holes, can be substantially more powerful than those created by supernovae. At present, Andromeda's black hole is not in a highly active state. It is not generating the kind of immense jets seen in quasars or other active galactic nuclei, but it is still producing winds. Even a weakly active black hole is capable of generating an outflow. As gas spirals toward the black hole, it heats up due to friction and magnetic interactions. This superheated gas then expands and pushes outward, creating a wind driven by pressure. Observations from X-ray telescopes have successfully detected these winds, revealing hot gas flowing out from Andromeda's core at speeds of several hundred miles per second. This wind is not a steady stream. It appears in bursts that correlate with the X-ray flares mentioned earlier. When the black hole undergoes a feeding event, it produces a stronger wind, and during its quieter phases, the wind subsides. The James Webb Space Telescope has added a new layer to our understanding by observing these winds in infrared light. Webb is able to see the cooler gas that X-ray telescopes cannot, revealing that the winds are more complex than previously imagined. They are not smooth. uniform flows but are instead structured into intricate filaments and bubbles. Some areas within the wind are dense, while others are almost entirely empty. These winds carry away the heavy elements forged inside stars and released by supernovae, such as carbon, oxygen, nitrogen, and iron. These elements are expelled from the galaxy and deposited into the intergalactic medium. Over billions of years, this process enriches the space between galaxies, creating a vast reservoir of material that can eventually fall back into a galaxy and fuel a new generation of star formation. At the same time, however, the winds also carry away material that could have formed stars. Every kilogram of gas that is blown out of the galaxy is one less kilogram available for making new stars. This establishes a delicate feedback mechanism. When star formation is high, more supernovae explode, which in turn creates stronger winds that expel gas and thereby reduce the rate of future star formation. The galaxy regulates itself. In Andromeda, the winds are currently at a moderate level. They are not strong enough to halt star formation completely, but they are significant enough to influence the galaxy's overall evolution. If the central black hole were to become more active, these winds would intensify. An actively feeding black hole can generate winds powerful enough to clear out the entire central region of gas, creating a dead zone where no new stars can be born. This may be the reason why Andromeda's core has relatively little star formation taking place, despite the presence of dense gas clouds. The winds from the black hole might be preventing that gas from collapsing under its own gravity. The raw material is there, but it is being constantly stirred by outflows, making it unable to settle down and fragment into new stars. When the Milky Way and Andromeda eventually collide, these winds will become dramatically more intense. The collision will funnel enormous quantities of gas toward the centers of both galaxies, causing their respective black holes to feed at much higher rates. The resulting winds could blow out a significant fraction of the gas from both galaxies, potentially shutting down star formation for hundreds of millions of years after the merger is complete. These are not gentle phenomena. They are cosmic-scale events that reshape the destinies of entire galaxies. And they are not the only mysterious signals coming from Andromeda's core. Neutrinos are often called ghost particles. They pass through matter almost as if it were not there. Every second, trillions of neutrinos are streaming through your body, originating from the core of our sun, from distant supernovae, from nuclear reactors, and from cosmic ray interactions in the atmosphere. Nearly all of them pass through the entire planet without interacting with a single atom. Detecting neutrinos requires enormous and highly specialized observatories. The IceCube Neutrino Observatory in Antarctica is one such facility, consisting of over 5,000 sensors buried deep in the ice, monitoring a cubic kilometer of frozen water. On the rare occasion that a neutrino collides with an atom in the ice, it produces a faint flash of blue light. IceCube is designed to detect these flashes and work backward to determine the neutrino's point of origin. The vast majority of neutrinos that IceCube detects come from our atmosphere or our sun. But every so often, the observatory detects high-energy neutrinos that have traveled from deep space. These astrophysical neutrinos carry energies millions of times higher than solar neutrinos. They are produced in the most violent environments the universe has to offer: supernova remnants, gamma-ray bursts, active galactic nuclei, and, it seems, from Andromeda. In 2006, IceCube registered a burst of high-energy neutrinos that came from the direction of the Andromeda Galaxy. The timing of this detection was quite remarkable. The neutrino burst was observed to occur at the same time as the first significant X-ray flare from Andromeda's central black hole, an event captured by the Chandra X-ray Observatory. Then, in 2013, the phenomenon repeated. A second burst of neutrinos arrived alongside another X-ray flare, and both emissions traced back to the same origin. This correlation carries deep significance for our understanding of galactic cores. Neutrinos are generated when particles with extremely high energy collide with either matter or radiation. Within an active galactic nucleus, protons can be accelerated to incredible velocities, approaching the speed of light. When these ultra-relativistic protons strike photons or other particles, they create particles known as pions. These pions then decay into muons and neutrinos, and subsequently, the muons decay into electrons and even more neutrinos. The fact that neutrinos reached our detectors at the same moment as X-rays strongly suggests they share a common source. Some powerful event at the heart of Andromeda is simultaneously generating X-rays and accelerating particles to energies sufficient for neutrino production. The most plausible explanation points to particle acceleration within the accretion disk swirling around the black hole, or perhaps within jets of material erupting from its poles. But a puzzle emerges from these observations. Andromeda's central black hole is not believed to be active enough to generate a detectable stream of neutrinos. The neutrino flux, measured by the IceCube Observatory, is consistent with that of a moderately active galactic nucleus, which is far more energetic than what X-ray observations of Andromeda would lead us to expect. This implies one of two things. Either the black hole is more active than it appears, or we are observing a rare and fleeting phenomenon. A recent analysis published in 2025 examined this correlation in great detail. The researchers were able to confirm that the two neutrino bursts are statistically significant and are genuinely associated with the Andromeda Galaxy. This is not a coincidence. Something within Andromeda's core is accelerating particles to extreme energies, producing both X-rays and neutrinos in the process. Several theories attempt to explain this. One idea is that the black hole is producing intermittent jets. These jets could be too faint or too narrowly focused to be detected by our radio telescopes, yet still powerful enough to accelerate particles and create neutrinos. When such a jet briefly activates, we would observe an X-ray flare and a neutrino burst. When it deactivates, the core would return to its quiet state. An alternative theory proposes that neutrinos are produced when large clouds of gas fall toward the black hole. As this gas spirals inward, powerful magnetic fields can accelerate some particles to ultra-high energies. These particles might then escape just before crossing the event horizon, flying outward to collide with surrounding gas and radiation, thereby producing neutrinos. This connection to neutrinos fundamentally transforms our understanding of Andromeda's supermassive black hole. We are no longer looking at a completely dormant object. Instead, we may be witnessing something in transition, a black hole that is beginning to awaken, starting to feed, and initiating the kind of high-energy phenomena that characterize active galactic nuclei. If this activity continues to build, Andromeda could evolve into a fully fledged active galaxy over the next few million years. Its central black hole would then blaze with radiation across the entire electromagnetic spectrum, and massive jets would extend for hundreds of thousands of light years into space. The galaxy would be transformed from a quiet spiral into one of the most luminous objects in our local group of galaxies. Neutrinos provide a singular view into this process. Unlike photons, which can be absorbed or scattered on their long journey through space, neutrinos travel in straight lines from their source directly to our detectors. They carry direct information about the particle acceleration processes occurring at the very edge of the black hole. Future neutrino observatories will be tasked with monitoring Andromeda more closely. If additional bursts are detected, and especially if they correlate with more X-ray flares, it will serve as confirmation that the black hole is indeed entering a new phase of activity. This would provide crucial data for understanding how supermassive black holes shift from dormant to active states. These elusive particles are messengers, and listening to them carefully could reshape our fundamental understanding of how galaxies evolve. The case of Andromeda is not an isolated one. It serves as a template, a nearby laboratory where we can study the very processes that unfold in galaxies all across the universe. What we learn from our closest galactic neighbor informs our knowledge of billions of other galaxies that are too distant to be studied in such intricate detail. The discovery that Andromeda has absorbed over 100 smaller galaxies in its lifetime confirms a fundamental principle of cosmic evolution. Galaxies grow through cannibalism. The largest galaxies we see in the universe today are not pristine structures that formed at their current size. They are colossal assemblies, built up over billions of years through a series of mergers and acquisitions. This process, known as hierarchical galaxy formation, is a cornerstone of modern cosmology. In the early universe, small galaxies formed first. Over cosmic time, these small galaxies merged to create larger ones, and those larger galaxies in turn merged to become even more massive. The process persists today, albeit at a reduced pace, as the expanding universe carries galaxies ever farther apart. Andromeda offers direct evidence supporting this model. The vast stellar streams in its halo are the fossil records of these past mergers. Each stream represents a galaxy that was torn apart and destroyed, its stars scattered throughout Andromeda's outer regions. By counting these streams and estimating the time of their formation, astronomers can piece together a history of Andromeda's growth. The chemical enrichment observed in Andromeda's stars tells another part of this story. The earliest galaxies had a low metallicity, as only hydrogen and helium were created in the Big Bang. Each subsequent generation of stars that lived and died contributed heavier elements to the galactic gas. By measuring the metallicity of stars in Andromeda, astronomers can determine when those stars formed and what the galaxy's chemical composition was at that time. Andromeda's relatively high metallicity when compared to the Milky Way suggests that it experienced a more intense period of star formation earlier in its history. It appears to have consumed its gas reserves more quickly, creating more massive stars that produced more supernovae, thereby enriching its interstellar medium at a faster rate. This observation supports models which suggest that larger galaxies evolved differently from their smaller counterparts. The activity level of Andromeda's black hole also informs our models of galaxy evolution. We now understand that nearly every large galaxy hosts a supermassive black hole at its center. We also know that the mass of this black hole is correlated with the mass of the galaxy's central bulge. This relationship suggests that black holes and their host galaxies co-evolve, each influencing the other's growth. When a black hole is actively feeding, it can produce powerful winds and jets that suppress star formation in the surrounding galaxy. This feedback mechanism is crucial, as it prevents galaxies from converting all of their available gas into stars too rapidly. Without this regulation, galaxies would likely burn out and cease to be active early in their life cycles. The winds from the black hole expel gas that would otherwise have formed new stars, effectively governing the galaxy's rate of growth. Andromeda's own evolution from a quiet to a more active state offers a live view of this cosmic process. A detectable rise in X-ray emissions and bursts of neutrinos suggests its central black hole is beginning to exert a much stronger influence on its galactic neighborhood. If this heightened activity continues to grow, it could eventually halt star formation within the galactic core, fundamentally reshaping Andromeda from a spiral galaxy, creating new stars into a quiescent elliptical one. The approaching collision with our own Milky Way presents an even more significant laboratory for study. Over billions of years, astronomers will observe a major galactic merger as it happens, providing the ultimate test for computer simulations that predict such events. We stand to learn how vast clouds of gas react during these collisions, how the birth of stars is either sparked or suppressed, the mechanics of how black holes interact and eventually combine, and how their surrounding dark matter halos merge. This insight will not be limited to our local galaxies. It will apply to every merger taking place across the cosmos. By studying the fate of Andromeda and the Milky Way, we are in fact learning about the universal principles of galaxy evolution. The James Webb Space Telescope, adds a crucial layer of infrared data to this picture, allowing us to see through veils of cosmic dust into regions that were invisible to all previous instruments. This new vision reveals once hidden nurseries of stars, complex chemical compositions, and cosmic structures that challenge our existing models. Every galaxy possesses its own unique story, and Andromeda's is a narrative of violence and expansion, of galactic cannibalism and subsequent renewal, centered on a slumbering giant that is now beginning to stir. It is a story that has been told countless times throughout the universe, and one that our own galaxy is destined to experience firsthand. The convergence of the Milky Way and Andromeda is not some isolated cosmic accident. It is a part of the magnificent cycle of galactic evolution that has been unfolding for over 13 billion years and is set to continue for hundreds of billions more. We are simply witnessing a single chapter in a story far grander than ourselves, a story written in the light of stars and the gravity of dark matter, in X-rays and neutrinos, in ancient streams of dust, gas, and stars. The universe is an inherently violent place, yet from that violence, creation emerges. And this leads to one final, tangible truth. If you look up into a clear autumn sky, far from the glare of city lights, you might just perceive it, a faint, hazy smudge of light within the constellation Cassiopeia. It is easy to miss if you do not know precisely where to look. That smudge is Andromeda, some 2.5 million light-years from Earth, yet just close enough to be seen with the unaided eye. You are observing light that departed from that galaxy at a time when our own ancestors were just beginning their human journey, long before the first cities were built, languages were written, or tools were crafted. For 2.5 million years, that ancient light has traveled across an incomprehensible void just to arrive in your eye this evening. And as you are watching it, one can imagine Andromeda watching back. Its trillion stars shine across the darkness, many of them surely hosting planets of their own. If life exists on those worlds, if civilizations have risen and fallen, they too might have gazed across the intergalactic gulf toward our galaxy, seeing the Milky Way as it was millions of years in their past. The James Webb Telescope has provided us with the most detailed view of Andromeda ever attained. We have peered directly into its core, seen the monster that lurks within, watched gas spiral inexorably toward the black hole, mapped stellar nurseries once hidden by dust, and detected signals that inspire both fascination and profound concern. What is unsettling to scientists is not the fact that Andromeda is headed our way. That has been known for more than a century. The truly alarming discovery, revealed by Webb, is the galaxy's current state of being. We see a black hole awakening, a surge in X-ray flares, and a stream of neutrinos pouring from the core. We see star formation accelerating in specific areas and galactic winds growing in power. These are all signs of an instability that our models had not predicted. Andromeda is changing, right now, in what constitutes real time by cosmic standards. The galaxy we observe today is not the same one we saw just 20 years ago. Its black hole is more active, and its core is more turbulent. Something fundamental is happening. When the collision does occur, whether in 4 billion years or 10 billion years, it will not be a gentle merger of two stable spirals. It will be the convergence of two dynamic, evolving systems, each already undergoing its own internal transformation. The violence of the encounter will be amplified by their active black holes, their disturbed gas dynamics, and their ongoing consumption of smaller satellite galaxies. Humanity will not be here to witness this event. Our species may not endure for the next few thousand years, much less for billions. Even if we did, spreading among the stars as a spacefaring civilization, we would face the end of our own world long before the galaxies meet. Our sun is destined to destroy its own planets in about 1 billion years. But the knowledge we are gathering about Andromeda is not just for us. It is a legacy for whoever comes next, for civilizations that might arise on other worlds, or for the distant descendants of humanity, whether biological or artificial, who will one day populate this galaxy. They will inherit this understanding. They will watch the collision unfold. They will witness the birth of the galaxy known as Milky Way. And they will remember that we were here first, that we looked to the night sky and asked questions, that we built telescopes to see into the hearts of distant galaxies, and that we uncovered the truth about our cosmic neighbor. Andromeda is coming. Its black hole is waking. The collision has, on the scale of their galactic halos, already begun. These are not theories, but facts, confirmed by observation, supported by data, and verified by multiple independent sources. The universe is larger than you can imagine, and it is more violent, more beautiful, and more terrifying, and we are a part of it all. Temporary specks on a small planet, orbiting an ordinary star, in a galaxy that will soon merge with another. In 4 billion years, the night sky will be transformed. Andromeda will fill the heavens. A new generation of stars will blaze into existence. The two black holes will dance together before becoming one. And from the remnants of two galaxies, a new cosmic structure will arise. That is our destiny, written in the motion of galaxies, as inevitable as gravity itself. The James Webb Telescope has shown us the future, and it is at once both magnificent and terrifying.